Hi, everyone. This presentation is entitled The Actuation of an Adaptive Tensegrity-based Roof Structure Using Continuous Cables. My name is Sychterz, and I am presenting this work on behalf of my student, Mr. Sagnik Paul. We are out of the University of Illinois, Urbana-Champaign. So firstly, this is a tensegrity structure, which is a pin-jointed system composed of bars and cables held together in a state of self-stress. The advantage of tensegrity structures is that they are lightweight, have a high strength to weight ratio, and they can easily be made to deploy. So tensegrity inspired large-scale infrastructure includes the La Plata Stadium in Argentina and the Kurilpa Bridge in Australia. We kind of know tensegrity structures mainly as the small models, as you may see on the top right, but our lab is challenging the infrastructure community to look at tensegrity structures and adaptive structures overall for looking at these lightweight structures as real solutions. So deriving the topology based on the hollow rope tensegrity bridge by Motro in 2006, using the top portion of the hollow tube, can this be made into a roof structure? And so we're going to be looking more so at the changing of the shape rather than deployability. And so it's about 150 centimeters wide and 400 centimeters, in length, with each module being approximately 100 centimeters. So as mentioned previously, it's not looking at deployment, it's looking at the curvature that can be obtained. So this will be in light of a stimulus, such as snow load, rain load, and the evacuation of snow off of a roof could be really useful, and allowing the roof to be, the elements of the roof to be sized a little bit smaller, and using that actuation to counteract those to remove the thing imposing the forces, as we've seen in this past couple winter and a few winters where there's snow buildup on roofs in the Midwest and the northern areas of the US and in Canada, can actually pose a lot of stress on roofs. So we're looking at nodes 11, 20, and 32 to be elevated, and we'll be changing the shape and evaluating different options for those particular nodes. It's pinned at the ends and rail supports on the sides, so it can allow some movement of the intermediate joints. So looking at some cases, the first one is if we have just a center node that was raised, the actuation takes place by the lengthening of the struts through like an actual piston that will be designed later. Right now it's a simulation base. We're in the beginning steps of the actual experimental process. But this allows two flat sections on the side, which is not ideal for precipitation evacuation. So case B, this is bimodal. This could be useful for trough and funneling water or snow loads, but that's not the point of this particular study. C is when we have all three of the center nodes elevated, and the actuation produces a flat top, which is not the best, but we're getting there. Case D and E, these are kind of more energy conscious cases. So we actuate half the number of struts, or we look at less actuation overall. So there's less height. So we're first going to evaluate the options based on effective position change, which is the sum of the change of position, the z-axis for nodes 11, 20, and 32 over the total actuated length. So we see that for case D, it's the best case scenario. So we have the most change, and then case E is the worst case scenario, so it has the least amount of change. And I'll go over why case B and C, even though it has the same value here, doesn't make the cut later on. So effective length change is the total length actuated minus the sum of actual length actuated over the total length actuated. So this percentage, we're looking for the lowest possible, and that's where case D shines. At 1.2% versus the worst case scenario, which is 7.9. So a lot of energy put in for not as much return. But this still produces a shape with that flat top, right? So we can then use differential actuation where 2 of the 4 struts are actuated 20% more. And this actually produces more of a constant curvature. And this is something that would be useful in terms of, snow melting and flowing off or sliding off the roof. And we'll be looking here at the Z effective and the L effective, so the actuated efficiency and the position efficiency are the same as case D. So we're still getting all the benefits, but now we have even a better shape. So moving forward with that, we look at the integration of continuous cables. So in the pink line here in diagonals on the right-hand side figure, across the modules will actually help alleviate the stresses, but doesn't actually negatively impact the position of any of the nodes. So we're allowing more flexibility without sacrificing all that, all the benefits we just discovered. So as you can see here, the comparison of the struts on the left-hand side and the cables on the right-hand side, the effect of having no continuous cables, so just point to point, is in blue. And then continuous cables, those pink lines, are here shown in orange. We see an overall decrease in the maximum forces in the elements, and overall in all of these elements, it's a general decrease in the demand. It also averages out over all the elements. So this is an extremely positive find. So moving forward, we see that with this dynamic relaxation model that we used for the tensegrity structure, is that we can find the shape of this tensegrity roof, and we can use it to find the optimal shape and integrate continuous elements, which helps balance out the axial forces in the structure so that we can reduce the peak axial loads. And so this will be moving forward into the experimental portion of this work very soon. Thanks for your attention.